Thank you, G. So let me actually arrange this a little bit so you can see the screen, right?
Yes.
Okay, great. Right, thanks for giving me the opportunity to talk. It's a good practice for me. Okay, so my name is Ceren. It's pronounced with a J as a Turkish name, right, for those who don't know me. And I'm an ITEM fellow here at the university, Harvard University. And today I'm going to tell you about how to break ergodicity, the mechanisms of ergodicity breaking in a chaotic quantum system. And this chaotic quantum system that we're going to have is going to be a spinor Bose-Einstein condensate. So spinor condensates are one of the most widely used like experimental platforms in cold atoms. And let's see, and I cannot. It seems to be stuck. Wait a second. Oh, okay. Sorry about that. Okay, let's see now. All right, it's working. Okay. Great. Okay. So I said that you're gonna stick with spinor condensate, and that's part of a cold atom systems. And cold atom systems, together with some other hardware, nowadays are called quantum synthetic matter. And the reason is because of their capability to simulate quantum matter and probe the fundamental physics, fundamental principles of physics. So some notable examples, definitely not limited to, but in the past few years, basically, we were able to like measure entanglement entropy and probe thermalization on closed quantum systems in optical lattices, the one that you see here. Also the pre-thermal many-body localization, again in optical lattices, and dynamical quantum phase transitions in ion traps, and spread of spatial temporal correlations in superconducting quantum processors. And maybe one of the most widely known nowadays, very popular hardware is Rydberg atom arrays. So these are ensemble of atoms excited to their Rydberg levels, and then they are trapped in optical traps so that they can be actually they can actually move around each other. So there is a lot of motion capability there. But on top of it, the Rydberg atoms, when we want to think about them, it's really like an atom excited to its the high principal number, so that they're also called giant atoms, for example. One of the first experiments in this Rydberg atom arrays is basically, they were basically seeing these oscillations, and after a quantum quench. In a non-integrable system like this one, typically what we expect is thermalization, but instead there were these well-defined oscillations. Later there was some like theory development for this to explain why there's such like well-defined robust oscillations, and that was really like the name of the model is PXP model, and it was really integrating this Rydberg blockade condition of the Rydberg atom arrays into the model, and finding like these special states. So maybe actually I want to be able to show these things, but what do you think? Since there are so many people on Zoom, should I be showing with like some sort of here or this way? On the computer, okay. So what I'm gonna do then, I'll just sit here. Okay. So laser pointer. Great. So the origin of these oscillations turn out to be these many-body quantum states embedded in the bulk of the spectrum. And these states, like, for example, these black states here that you see, are low entropy, non-chaotic, and ETH violating many-body states. Here, ETH is the Eigenstate Thermalization Hypothesis. These states are negligible in the thermodynamic limit, meaning like their numbers are increasing polynomially while the Hilbert space dimension is increasing exponentially. And depending on the model, for example, this PXP model that explains the Rydberg atom array results, they could be equally spaced across the many-body spectrum, like the ones you're seeing here. So that means if you actually prepare an initial state that can overlap with these spatial states, you can actually have these well-defined oscillations. So here, what you see, by the way, is really like the overlap of the eigenbases with the Z2 product state. So it's a simple, it turns out that the initial state you need to actually prepare to probe this physics turn out to be product states that can be conveniently prepared in the lab. So that was the reason why it was measured first. So these people called this phenomena quantum many-body scar. But where did that come from? Where did they get their inspiration? All right, I'm stuck again. Let's see. Yes, okay, great. They got their inspiration from an older concept, quantum scar. And this concept goes back to 1984 to Rick Heller. And a quantum scar is a quantum eigenstate where there is a higher probability density around an unstable periodic orbit that lives in the phase space of the model. So immediately you can see in the criteria of quantum scars, the model has to have a phase space. And this orbit has to be unstable in the sense that when you calculate this Lyapunov exponent, it has to be a positive Lyapunov exponent. So it will be unstable to perturbations on this around this trajectory. And this orbit, the scurrying unstable periodic orbit also has to be embedded in a chaotic region. So this is basically the definition of quantum scar. And if you, for example, initiate a wave packet on this unstable periodic orbit or UPO, you would see well-defined state fidelity. That means the overlap between a time-evolved state with the initial state is going to show revivals. So these two concepts, they're both like the zero measure concepts in their respective phase spaces. But maybe the inspiration really came from there, like the connection between two. However, even though like the now like nowadays it's been assumed that like the QMBS, quantum many-body scars, are many-body generalization of quantum scars. Whether there is really a connection is not really an answered question. Yes.
So they have high probability to go around that area.
Yes.
But they are. So you are saying they are also unstable. So if you kick them, then they
yes.
go away.
Yeah. So basically, the quantum eigenstate itself shows this higher probability around the unstable periodic orbits in a respective phase space. And if you look at the classical calculation, indeed, like those are coming from the UPOs, meaning exactly what you said, like they tend to diverge if you initiate motion around them or on them and perturb it. Yeah. So we are really questioning the possible connection between those two. So whether there's really a connection between them. So there aren't actually many works on this. The existing works are really on the PXP model. And PXP model is actually a model that doesn't have a semi-classical limit. So then these people basically need to come up with some effective phase spaces, and that's basically done with these TDVP methods. So you write down equations of motions based on the time-dependent variational principle, so tensor network methods. And from there, you can define certain effective phase spaces and study those effective phase spaces. But in none of these works, actually, there was no QMBS was found corresponding to a UPO embedded in a chaotic phase space. And in fact, this in one of these last works here, what they had found was a QMBS was associated with a stable periodic orbit, embedded in a mixed phase space. And stable periodic orbit, what I really mean there is the Lyapunov exponent is 0, so it is in a stable regular region. Okay, so in that sense, the relation of QMBS to quantum scars and also the regular states remains unclear. And we wanted to bring a fresh perspective to this question by studying a model that's really not studied in this context before, which is spinor condensates. The model itself, the advantage of the model is that it has a semiclassical limit. There is a mean field limit associated with it, so that we can actually really go to the phase space, true phase space, and understand the phase space properties. And then using the classical quantum correspondence, we can go back to the spectral properties and truly understand what's going on. So I will first very briefly tell you what we achieved in this work, and then I'll get into the details. But basically, we found this UPOs card eigenstates in a spinor condensate. So they look like this in the coherent state basis. That you can see the quantum eigenstate here has enhanced probability density around the UPOs. We also find that, yes. Yes, unstable periodic orbit. It's a periodic orbit in the phase space, but its Lyapunov exponent is positive. That tells you about the instability of the periodic orbit. So
by phase space, you mean X and P.
So if you have, like, say, a quantum billiard model, yes, that will be an XMP typically. But here, this in the spinor condensate, our phase space is in terms of other parameters that I'll explain in a bit. Yes, it's basically we're working in the coherent state basis, which is the most classical, here.
And you, in the previous slide, you say you want to differentiate quantum scar versus quantum many body scar.
I do differentiate them because quantum scar has its own well-defined definition.
So for a quantum scar, you add more particles that they don't become quantum many body.
Yeah, that's a very good question. So that's I mean, normally right now the model that we are studying has already many particles in them. It's a condensate of many atoms. But as I will show, we are actually focusing on a certain limit where the model becomes not truly single particle, it becomes few particles. So it has the sweet spot between a single particle and many body system that then actually it helps us to actually see these connections better. But yeah, it's a very interesting question. Like, you take a single particle system with a quantum scar and you extend that to many body, do you get a QMBS, quantum many body scar? That's exactly the question that we've been asking here. Yes. Okay, so we also find that the spinor condensate that I'm going to explain in a second hosts both quantum scars and regular states. And regular states, like, they're associated with stable periodic orbits. Okay, so for example, in a Poincare section in our phase space, these are stable periodic orbits because their Lyapunov exponent is 0. Okay, and in general, what we find in this work that spectral properties of regular states actually suggest a link to QMBS, not quantum scars. Okay, so let me now get into the details. So spinor condensate Hamiltonian, a usual spinor condensate Hamiltonian that you see here, where the kinetic term, and you see the kinetic energy part and trap potential, and then we have the interactions, the density interactions, which is captured by the number operator for your atoms, and then the angular momentum operator here. Because I'm sticking with a spin 1 spinor condensate, this angular momentum operator is simply spin 1 operator. So there are many atomic species has been studied now experimentally all around the world, but typically people stick with rubidium and sodium species, and that gives you spin 1, for example, spin 1 spinor condensate. And for these rubidium and sodium species, there is a imbalance, like in terms of the strength of these interactions, and that exactly gives us this single mode approximation. And under the single mode approximation, a wave function can be factorized into a spin part and the spatial part. And the spatial part of these different spin components are the same, homogeneous, especially around the center of the trap, so that we can actually take it out and end up having just a spin system, a spin Hamiltonian. In this spin Hamiltonian, so we have the density interactions. We have also famously these spin mixing interactions that have been studied like for maybe many decades now. And typically in an experimental system, we have also a magnetic field applied here, which brings the linear and quadratic Zeeman effects. So this system here, together with its magnetic fields, etc., is an integrable system. And first of all, we need to have a chaotic system. We want to induce chaos. For this, we need to break the integrability. So we imagine having adding 2 rotating in-plane fields first, and then we do a change of rotation and in the second step. And under large magnetic field condition, we end up having these simpler Hamiltonian here. The green part is our interaction part, and then the red part is what's breaking the integrability in the system. It's the mode mixing part, as you can see. So these are annihilation creation operators for your spin plus, minus, and 0 operators. Yes.
What are P and Q?
Yeah, so P is the strength of your linear Zeeman effect. So you have, because under the magnetic field, you would induce linear and quadratic Zeeman effects. So the P is for the linear Zeeman and the Q is for the quadratic Zeeman fields. Basically, those are field strengths. But what we do is we just do some unitary transformations to get rid of those things. Yeah, in the end, what we end up having is the interaction part, which is really simple, like density interactions. And then the P becomes the most important tuning parameter here, which is really the strength of your in-plane laser field. So this can be done in an experiment and tuned. So the nice thing about this simple model is even with a small P, like 0.05, we end up having a diverging density of states in the middle of the spectrum, okay? So that diverging of density states will help us to induce chaotic behavior, okay? Yeah.
Like, so Q disappeared.
Yes, because so what I do in the end is we have this large magnetic field condition. So under that condition, actually, we can have the simpler.
Q is effectively infinity.
Q is effectively infinity. Yeah, you can take it like this.
So you want me to?
Yes, so that we are actually at the level of energy level of P, and that affects the Hamiltonian. Yes. Then it is an integrable model. It looks pretty regular. Now I'm going to show you what happens with the small p, because that's really the interesting point where you can have mixed spectrum. So, I mean, I'm gonna show it, like I already showed you Poincare section, right? It looked actually mixed phase space. Indeed, we have a mixed phase space in the classical limit of the model. And in correspondence with that, we have a mixed spectrum too. And that's what we do next. So we first look at the entanglement entropy. So let me note that this is a condensate of atoms, and particularly here, I think we're using 200 atoms. And the Hilbert space dimension scales quadratically in the particle, in the atom number, okay, n square, so it's not n. And on top of it, because this is kind of an all-to-all interaction system, it's a gas, we don't have bipartite entanglement entropy. So what we have here, what we're calculating, is a particle entanglement entropy. So it tells you how much of one atom is entangled with the rest of the condensate. And what we see in this entanglement entropy plot is that most of the states are saturating the maximum entropy. And in fact, they are showing level repulsion. So these are chaotic states, okay? And then there are also some other states, the second type here, looks structured in a very regular way, and they actually show level bunching, showing their nearest neighbor energy level statistics shows Poisson statistics, okay?
That is about the notation. So you write like rho 1 JK. The J and the K index.
Those are the spin.
Spin.
Yes, spin indices, right? And then you have basically one body density matrix here.
Right. Then but you mentioned this is like entanglement between particle and condensate. But from JK, you said there are like spin indices. Then it looks like it's the entanglement between different spins.
So
I'm having trouble understand like.
yeah, this is a different type of entanglement entropy. So there are actually two entanglement entropies that we could calculate. One of them is this, and the other one is mode entanglement entropy. So the one that you're telling me is actually kind of reminding me of mode entanglement entropy, where you need to trace out one of the modes, like say like spin 1. You trace out the spin 1 and you end up just seeing like the entanglement of the spin 1 to the rest of the spins, like 0 and -1. But here, what we're calculating, this one body density matrix is already, you can see it's already mixed actually when you write this down. So that's the reason, for example, you can have non-zero values for this entanglement entropy here. Yeah. Okay, so let me continue. We also look at the thermalization properties of these states. These higher entropy bands, the ETH is satisfied, while the lower these like structured states, like ETH is violated. For these, we look at the we need to choose a local order parameter, sorry, local observable. And this particular observable we choose is the number of spin 0 atoms. That's what's typically measured in spinor experiments. And you can already see how eigenstate expectation values look like. So this is basically these chaotic states kind of form this kind of like band-like structure here. And ETH is satisfied. So we look at both the diagonal and off-diagonal ETH and show this. Okay, so on top of this, we do dynamics. So if we initiate the dynamics on the let's say the regular region, okay, so these regular states, we see basically well-defined oscillations for a long time. So these are robust oscillations in the population N0. And the fidelity of the time evolved state with the initial state also shows very high revivals. So, okay, and okay, yeah. So and the other thing to add here. So if I actually initiate the dynamics on this higher band here in the chaotic part, then we don't see the revivals. There's no revivals, and also we see the thermalization. That's the reason why we call this like higher band here ergodic band of states or chaotic band of states. And we call these states here like the structures say regular states. Partially the naming really comes from the fact that these states are also associated with stable periodic orbits, as I will explain in a second. Okay, but before that, let me also mention that we looked for the origin of these regular states. And it turns out that they are originating from the integrability in the model. And there is some approximate spectrum generating algebra that we could write to actually generate them. So let me first tell you how this happens. First of all, we noticed that for these specific states, there is an imbalance between the spin 1 and -1 atom numbers. So that imbalance puts one of these modes, like a suppressed mode, which we can then simply replace the operator for that with its eigenvalue. That reduces a 3-mode Hamiltonian that we had to a 2-mode Hamiltonian, which is an integrable model. So we call these regular Hamiltonian with just 2-mode coupling. So if we diagonalize this Hamiltonian, we actually see these circles here, the red circles, and we can actually like see that this can explain these states actually explains the all regular states. The all regular states are these dots here. Okay, so but note that only a few of them here can be explained. There are still some of them not explained. And that's because of the finite size effects. To show that, we just like go to 2000 atom number for these like integrable model and diagonalize it, and then take just one in each like 10 eigenstates, and that gives us like the entire regular state here. So these are basically the pluses here. So on top of it, if you start with this Hamiltonian and write it in the spin picture and then linearize it, you can actually come up with these spectrum generating algebras. I'm not sharing like the expressions for these operators that generate these states, because they're not especially like illuminating, but you can see them in our supplementary material if you like to. But I'll explain like how you can think about them. So you can see that there are these n towers. Okay, sorry, n towers. And each tower, there is a number of states that's proportional to n states. So in each tower, basically, like to go up to the tower, you need to stay in the same n minus block, because that is the background mode, right? And in order to like generate them, you need to exchange excitation in this two mode effective system. So that actually gives you this tower approximately. You can see it's not capturing the entire thing. And then K2 here basically generates the different towers. So you move between different n minus blocks. Okay. So basically what this shows that there is a spectrum, approximate spectrum generating algebra, which is the one that people generally write for quantum many-body scars. Okay. So all in all, I showed you certain criteria for regular states that we call regular states, but they're all the criteria for QMBS too, quantum many-body scars too. It checks boxes for all of them except one, which is basically that these regular states are not disappearing in the thermodynamic limit. They're not zero measure, and they are actually associated with stable periodic orbits, and that's why we call them regular states. Yes, they're regular states. Yes, we call these regular states. Even though they check boxes for QMBS, still let me note that like the number of these regular states increase proportional to n square, while the Hilbert space dimension also increases proportional to n square. So for QMBS, that there is that difference. The number of QMBS increases polynomially, while the Hilbert space dimension increases exponentially. Say it again. I didn't hear exactly. Yes. In the middle of the spectrum, there are a couple of low integral states. Exactly. Are these states unused to them? They are what? Are these states same as them? Yeah, that's a good question. So what we are showing here, the spectral properties are very much the same, right? But we don't call them QMBS because at least one criteria is not satisfied. Their numbers are increasing proportionally to the Hilbert space dimension. So that's one thing that they're differentiating from each other. But it's very curious, the fact that regular states actually have this many like resembling properties with the QMBS. So one interesting question that we are dealing with right now, for example, if we extend the system to a quantum many-body system where the Hilbert space dimension increases exponentially, whether we're going to be able to keep this regular states, are they going to turn into QMBS? So they're already sort of smelling like QMBS, but we still want to differentiate them, like just to be careful. Yeah. I would like how the number of states increase n squared. Yes. Yeah. So it scales as n square. Yes, there is of course a proportionally constant, which is small. But that's the reason why, like when you look at like one system size, their numbers are small compared to the other states.
So how does the low-time space in the PXP models deal with this?
Polynomially, yeah, yes.
So this
It's similar actually, right? But there the difference is the Hilbert space dimension increases exponentially. In a PXP model. Yes, that's the difference.
so here in the Hilbert space,
Quadratic as well.
I see. So the
Yeah.
number of this integrable space increases the same way as the Hilbert space.
Exactly. Exactly. Yeah. Yeah.
Oh.
Yes.
The middle, the bottom is fidelity.
Yes, that's the fidelity.
Oh, I actually have two questions. It looks like the fidelity can drop all the way to zero.
It will eventually.
Like Twin Peaks.
Yes, it will eventually. So it's not because you start this from a state, right? So you start this from like a low entropy state, first of all, but you never actually just like overlap with say two states so that you can just go back and forth between these two states. It overlaps with like some region here on the regular region. So you have multiple
Those
states.
are particle.
These are eigenstates. So yes,
Oh.
so they're all each perpendicular to orthogonal to each other.
But besides the period.
Yeah, so that's a good question. That actually what decides the period, it turns out to be related to the phase space properties, because these are related to the stable periodic orbits. So
Right, so like in the Hamiltonian, like which parameter can we tune to make the period?
yeah, so for this, I think the best thing to look at is a regular this integrable Hamiltonian, which is two-body like Hamiltonian, right? So it needs to be, I cannot tell you immediately what it does, but this is kind of like a pendulum-like behavior.
Already integrable model.
You can see it already from the integrable model.
Interactions to make it more competitive.
Yeah, so I mean, normally this is not the model that we have, right? We have like a 3-mode model, which in itself has interactions. But
so the 3 years one.
that's the original model that we have, right? We are just basically getting this. This is an approximation to that to be able to explain the origin of the regular states, right? Right. Okay. So I told you that this model is interesting because it has a phase space, right? So maybe let me tell you about that. So for this, we need to write down the wave function in the coherent state basis. And you can see here, like we have 3 spin indices. So it comes with the amplitudes and the irrelevant phases, but then the global phases is irrelevant. So then we take that out. And on top of it, there is U1 symmetry. So total number of atoms is conserved. That basically gives us like 4 independent parameters. Eta and theta are some relevant phases, and N0 is the number density for the spin 0 atoms, and the M is the magnetization density. So that defines our phase space. It's a 4-dimensional phase space. And simply like with this parameterization, we can write down the mean field energy, for example, as you see here. And on top of it, we can write down the Lagrangian and derive the equations of motion. So this is a 4-dimensional phase space that can host chaos, right? And to find the general solutions, we need to numerically solve these. We basically study the Poincare sections coming from here. A Poincare section gives you a look to the phase space, right? So you need to have a cut. In this particular case, we are basically looking at a N0 theta plane, okay? And the first thing that we realize is a mixed phase space, okay? So it's a mixed phase space. Why? Because this region here is chaotic. You can see it from the color codes with the Lyapunov exponent. These are all chaotic trajectories. And to our surprise, there is an unstable periodic orbit living in the middle of this. And on this regular region with the stable periodic orbits, they have 0 Lyapunov exponents. So after studying yes.
And it was so why did you introduce the coherent state? Is it eigenstate of the Hamiltonian or?
No, it's not eigenstate of a Hamiltonian, but so we want to go to the mean field limit, right? So because that is where our like phase space lies, that's our classical limit. Really, there has to be a way to go to classical limit. And in this particular case, if you take the atom number to thermodynamic limit, that gives you a valid phase space. And a way of parameterization is really through defining this coherent state space.
So the introduction of the coherent state to field phase space.
Exactly. Yes.
But it's not eigenstates of the.
It is not the no. It's not the eigenstates of my Hamiltonian. Yeah. Not necessarily. There could be a particular region of the spectrum where like some states could be written like purely like coherent states, but not typically. It's not. Yeah. And coherent states are typically overcomplete. So okay. So now I want to use this classical quantum correspondence and see how the phase space is affecting my spectrum, okay? Quantum spectrum. For this, we fix the energy density. So for all these Poincare sections that I forgot to tell you that we're actually fixing the energy too, okay? So then after fixing energy, I take like a state that corresponds to that energy, but in the regular region, and calculate the semi-distribution of this eigenstate in the coherent state basis. And let me note that because it's a 4-dimensional phase space, we need to integrate out the other 2 dimensions here. And that gives me this kind of Husimi distribution in the phase space. And you can already see the signature of the stable periodic orbits here. So from here, we're able to actually associate the regular states to stable periodic orbits. And the next one in the same energy, but we're taking a state in the chaotic region. And we find that the Husimi distribution is showing the scarring of the quantum eigenstate. And it's exactly explainable with the UPO at this energy. And consistently with this, we're seeing a fidelity revival, the first fidelity revival being robust. And by robust, what I mean is like with respect to the atom number. So if we go to like 1,000 atoms, like a microscopic number of atoms that you can have in a condensate actually today, and you will be able to see this fidelity. The orbit, you mean? Because you calculate the Lyapunov exponent for this orbit, and it is a positive value. So that tells you the instability of the.
At the circle also cuts the gray area. The area saying that it's not defined.
This you mean this area here? That.
Yeah.
Oh, these areas here. Those are actually, there is no density of states there. That's why we made them green. Made them gray, not to confuse. So you can also see here there is no density of states around here too. So okay. Yes.
Why is the fidelity plot so different
from the other one?
Sure.
Yeah.
The previous one is like periodic sense.
Because those were like, I'm choosing an initial state such that it overlaps with the regular states, and regular states are stable, and they actually do give like a well-defined oscillations, robust oscillations. While here, like I am choosing the initial state so that it overlaps here around this chaotic region here. So I'm not only overlapping with the quantum scar states, I'm overlapping with many of them, in fact. Oh. And that also means that given the fact that this is a high entropy region and thermalizing dynamics, eventually my dynamics is going to thermalize. And I'm not really going to have that kind of well-defined oscillations for a long time.
But then why is there still one peak? Like if it's like it overlaps with several of them.
Yeah, but like still, your eigenstate occupation numbers still like have some sort of distribution, right? So if it's mainly like overlapping with the quantum scar state, that means you're gonna first, like, you're gonna mostly see the effect of this state here, and then like the other contributions are gonna come in
First peak is from the
from
star,
this.
and
Yes.
other states start or kill the.
Yeah, eventually it kills it because there is some the destructive interference going on, right, between these between these states, quantum states. But you can still actually have some sort of the frequency here, and that frequency is actually UPO frequency. So that's actually one way of understanding this like revival attempts are really coming because of the UPO.
So producers prepare them in different initial states.
Yes.
It's the same Hamiltonian, and then you just pick different.
You can prepare any state, doesn't have to be an eigenstate of the Hamiltonian, and it shouldn't be actually. Right. So for example, for regular states, we prepare a Fock state that turns out to be working well with the probing the regular states. But for these scarce states, you need to prepare a coherent state, which is again experimentally preparable. So though I need to say a very fine-tuned state. So okay. So one question was actually that we had, if we increase P, can we make the probe of these quantum scars better in the dynamics? And it turns out to be the case, really. So if we increase the P to 0.5, let me tell you first that the regular states disappear. So now you have like the really all high entropy states, but there's still scarring in this high entropy region. So some of the states are scarred, and in accordance with that, we see like the first revival amplitude increases to 0.5, and then we are able to also get second and third harmonics here, pretty robust as well. So the local dynamics, local observable dynamics show again like oscillations, but eventually thermalizing to microcanonical ensemble. Hence, these states satisfy ETH, right? And again, if you look at the phase space, we can see that the unstable periodic orbit is actually embedded in the middle of a chaotic region, and the Husimi distribution of these states actually do capture this scarring. Okay, so I have, I guess, around how many minutes? 15? 10 or something. Okay, actually, I need only 10 minutes probably. So let me also note that like there isn't just one isolated UPO in this model. There are actually a family of UPOs. Okay, so at every energy in the middle of a spectrum, you actually have a UPO, and that causes high degree of scarring of the quantum eigenstates. So for this reason, for example, we define the scarness figure of merit. The numerator here tells you the overlap of an eigenstate at an energy, a specific energy, with the UPO, okay, coherent states around the UPO. And the numerator is just like, denominator is just standing as a normalization, because in the end, we look at this dn with respect to many different energies. So in the denominator, basically what we do, we construct what we call an ergodic state, which is a superposition of coherent states along the trajectory of a chaotic trajectory taken randomly in the phase space. And when we look at this across the energy, we find the histogram, which is biased, where the mean is greater than 1. That tells you that most of these states are actually scarred to a degree. So, for example, this first one that I was showing you, it was a strongly scarred state. It has like a scarness figure of merit 2.1 or something like that. While like there could be states like this, again, the same energy, right? But it's this like square state here. And it's weakly scarred because its dn is like around 1.2 or something like that. We expect like the one here representing like the most random that we could have. So anything bigger than 1 tells us that there is lots of scarring going on. Okay, so let me just wrap up. What we found is chaotic spinor condensates could host unstable periodic orbits in their phase space, which gives rise to these quantum scars. Okay. These same system can also hold stable periodic orbits in their phase space, which gives rise to regular states in the quantum eigenbases. And regular and scarce states are not only distinct in their phase space, but their spectral properties are pretty different too. Just to recap, regular states, we found they were low in entropy, violates ETH, so they don't thermalize, show Poisson and nearest neighbor level statistics, and they're associated with stable periodic orbits, giving rise to robust oscillations in time. While the quantum scarce states are embedded in this high entropy band, they satisfy ETH. Like when you take as an ensemble of this entire area, then you see the ETH. And Wigner-Dyson, we see Wigner-Dyson nearest neighbor energy level statistics, and then they do actually originate really from the unstable periodic orbit, so they are truly quantum scarce. So another thing, I guess, the spectral properties of UPOs scarred eigenstates are very different from the criteria of QMBS, so quantum many-body scarce. And in fact, the regular states are more reminiscent of the quantum many-body scarce. So this work is basically gave us a way to understand these connections between QMBS, regular states, and quantum scarce. And then we started to think about like whether we can actually take this to a many-body system, understanding all these ideas, whether we can actually do many-body generalization of a quantum scarce. And this part is really just a teaser at this point. So yes, go ahead. Yes.
So it's not the many-body the so-called many-body is not close to the
scarce. It seems so. At least from more work, that's what we're understanding. Yeah. And now we want to actually see whether we can make a many-body generalization of quantum scarce. So that's the recent thing that we're doing.
So you found the states in the PXP model.
Yes, so those are okay. As everybody's calling is their QMBS, right? So but whether they are actually more related to regular states or quantum scarce, it seems to me that they're actually more related to regular states. But really the only way to show this is through these effective phase spaces that people been working out. And honestly, like if you work with like a generic effective phase space, like not like say like constrain yourself at 2D or something, like a 3D or 4D, indeed like the results coming out there that QMBS is associated with stable periodic orbits.
It's still not clear.
I don't think it's clear. Yeah. For in the context of PXP model, it's definitely not clear because also like PXP model itself doesn't have a semiclassical limit. It's tough. In our model, at least we have hope that like if we can have the many-body model while still keeping the mean field, we can at least still talk about the phase space that lies. Of course, the question whether the quantum many-body states are going to be faithful to that phase space. They won't eventually, but still we can try to understand its effect on the quantum many-body dynamics, and that's what we are now doing. And that's what I'm just going to very quickly like give you a flavor of it, and then finish up. So we wanted to find a route to QMBS, but associated with a UPO, okay, embedded in a chaotic phase space. So really the generalization of quantum scarce. So there might be different routes of doing this, right? So for example, one could break the single mode approximation, introduce back the spatial part of the wave function. That will require ab initio calculations with Gross-Pitevsky equations. But the other, for example, way of doing this, we can just take the interactions, all-to-all interactions, and introduce a range to the interactions in the model, in the spin model. So the first one is not really my cup of tea. So the second one is what I'm used to doing. That's why we follow with that. And for example, we write down these kind of Hamiltonian that you see here, based on the model that we've just chatted about in the last month, hour. So here you can see there's Heisenberg type of interactions, but with some finite range. The UD captures that finite range of interactions. And for example, in the nearest neighbor limit, which is the one that we are really focusing on, the UD is non-zero only for d is equal to 1, right? So it's just nearest neighbor. And then one has to choose the normalization factor such that the energy remains extensive, so that we can actually talk about a mean field limit. The other terms are really coming from, if you remember the linear and quadratic Zeeman terms. So when we actually generalize it, these kind of terms come up too, and they correspond to a field, magnetic field in the z direction, and then a quadratic term, which is an on-site term, and also our transverse field P, proportional to P. So this is the starting Hamiltonian that we have, but of course we apply a certain transformations, etc., to work with them. But eventually the picture stays the same. So what we do here, basically, now we have a chain of spin 1 atoms. So each side has a spin 1 atom in it, and they're interacting with each other. So what we did here, basically, now, because we want to still talk about the coherent states, now we have many coherent states, and the way we construct them is just a simple tensor product of coherent states at each site. Okay, so these are basically product states, and we look at the bipartite entanglement entropy. Now, because we have a chain, we can talk about the bipartite entanglement entropy, and we see the usual arc. So, and then we also confirm that these states are actually volume law scaling states. And when we look at some of these states, for example, the red dots that's shown here, when we look at their Husimi distribution, we do see that these quantum many-body states seem to be scarred with some periodic orbits, and these periodic orbits are unstable periodic orbits embedded in chaotic region. That's again in the mean field, of course, right? So, and on top of it, for example, we can look at the overlap of the eigenbases with these many-body coherent states. And when we do this, we see a certain structure in the eigenbases. So this is more like a similar thing that what people do in the QMBS community, but they look at the overlap of the eigenbases with, say, a Z2 state. That's also a product state, right? So the nail state. But here we need to look at a many-body coherent state, okay? So that we can actually still have the connection to the mean field. We also do some dynamics and see that the effect of these orbits are actually imprinted in the dynamics too, up to a certain time. After that time, they thermalize, the dynamics thermalize as expected, again, because these states are embedded in the high entropy region. But what happens there are these well-defined oscillations. So you can see with the ED, and then we also do infinite TEBD, time evolving block decimation, so tensor network methods. And with the infinite version, we can see that these oscillations don't go away, so they're not finite size effect. So maybe just to wrap up, so basically we see this volume law entanglement entropy, which is pretty different from the QMBS that we know of so far, and thermalizing dynamics. And interestingly, early time oscillation frequency of these dynamics here matches the UPO frequency. So basically the quantum many-body dynamics seem to be still affected in its early time by this phase space results. And we do have actually an analytical expression for this oscillation frequency. And we can predict this analytically. So we're still working on this, but we're very excited. It seems to be a new type of QMBS. So hopefully we can actually make these connections better and differentiation of different QMBS from each other. Of course, this work wouldn't happen without this excellent team. Bertrand, a postdoc fellow at ETH, also the main driving person here in these works. Also Andrea and Simos, also postdocs at Harvard. So if you have any questions, just reach out to me. I'm around here. Also, you can reach out to me on email. And this work here, the first part of the talk, basically the main part of the talk, you can find it in this archive. And hopefully the last bit is going to come out soon. Yeah, thank you very much.
Any questions from Zoom?
Thanks.
Oh, yeah.
So if you go back to the summary table,
Summary table, yeah,
yeah.
yes,
So, when you say low or high entropy, you mean, in integrable entropy?
yes,
Okay,
yes.
so, does the integrable entropy here imply some kind of correlation in your system? Like, if you flip a spin one,
Mhm.
will cause more disturbance to like spin zero or something.
So the entanglement entropy that we calculate is based on the eigenstates. So we calculate each entanglement entropy associated with an eigenstate. So I don't know what that would mean exactly if you like perturb like one spin and what would happen.
So it doesn't, like, there is no like trivial invocation.
I don't think
correlation
so.
Inside your system.
I don't see it at least. Yeah.
And also, like, since one place of the states violate EDH and the other kind of satisfy. And you are saying usually when you prepare, you kind of get a random state, right?
Mhm.
The random state may have these two groups, kind of.
Indeed. You.
Right, so then,
Uh-huh.
for like random peak state, what will happen? Like some of them violate EDH, some of them follow.
This is a very interesting question. This is basically a result of a mixed spectrum. So yeah, so right. I mean, it's actually, I think the very interesting thing about this model is that it has a mixed spectrum. So typically what we find in models that they're either like satisfying their Dyson statistics, it's a chaotic model, or they show Poisson statistics, it's an integrable model. Right? This is actually in between with these different elements of it. And indeed, if you prepare a state that overlaps both of them, which is typically like some state, like mostly states are going to overlap with both of them, then basically what you're going to see in the dynamics is the effect of both.
Oh,
But eventually I would say like if the if mainly it's dominated by the chaotic region, likely you're going to see some sort of thermalization.
I think the integrable system is well the definition of violate states.
What states?
Integrable system is well.
Yes, yes. I mean, because in the end they do originate from integrable Hamiltonians, the regular states. Yeah.
Regular states includes integrable system at this model.
So I think probably regular states are really the states in the integrable model I would think of. But here the interesting thing, you find them in a chaotic model basically. So that's really again coming from the mixedness, huh? One could see it that way, or I mean, the other way of seeing it is like when P is equal to 0, the model is integrable already. So what you're doing is like when you break you're like weakly breaking integrability really, so that they stay there. So when you go really away from this limit, the special limits, P is equal to 0.5 or so, they all disappear eventually. Yeah, so they're not there anymore.
So the regular states disappear.
Yes. No, P is increasing, regular states disappear.
Oh, okay.
Yeah.
This regular states close to the integrability.
Exactly. Their integrability effect, basically. Okay.
Is there any question from the Zoom? So if not, let's thank Ceren again for the wonderful talk.
Thank you.
Mhm.
Okay.